In this video we're going to see junction width calculation and concepts related to it. So let us consider the figures here. The first one is charge distribution inside a Pn junction and corresponding electric field distribution and the potential inside the Pn junction corresponding to these distributions. Now these distributions we have discussed in the previous video on Pn junction, right? So taking this as a starting point, we are going to derive what is the junction width. Now let us define what we say as junction width, which is equal to xn plus xp. As we have seen here, this is xn and this is xp. I'm taking the magnitudes, okay? So this is called junction width. This width is nothing but this is the width over which we have depleted region. It means the mobile carriers are depleted and we have only immobile charges which are fixed in the lattice which are staying there, okay? So this is what is defined as width, and now let us start the derivation, okay? So to start with, what is the area under this electric field distribution curve? This looks like a triangle, right? So we can write it as half times base times height. So height we know, I'm going to take magnitudes, okay? So Q times NA divided by epsilon times XP, okay? This is height, okay? Half times height times base. Base is equal to this, which is nothing but xn plus xp, which is W. And this whole area will be equal to V naught. That's nothing but integrating the electric field curve with a minus sign, where we have seen E equals minus del V. So V is written as minus E dx here. As we are seeing one dimension, so we are taking x. So from that we are going to have this V naught equals half times QNA XP over epsilon times W. Now from this curve we saw that the positive charge should be equal to the amount of negative charge. So if we take an equation from that, we can write Q times ND times Xn will be equal to Q times NA times XP. Okay, so Q cancel. We have an equation here. So in terms of W, we know that W equals Xn plus XP, and we know equality like this. So can we write Xn in terms of W and XP in terms of W? So if we rewrite these from these two equations, okay, let me rub this off, okay. So Xn can be written as NA over NA plus ND times W, and XP can be written as ND over NA plus ND times W. So if we use this, we have XP here. Let me take XP from here and plug it in there. So we'll have half times QNA over epsilon times ND over NA plus ND times W. And we have another W, which is equal to V naught. We have W square, which we rewrite it. If we rewrite it, we have 2 epsilon V naught over Q times NA plus ND over NAND. Okay, this is the equation. So if we rewrite it, W equals 2 epsilon V naught over Q times 1 by NA plus 1 by ND. We can rewrite it like this, whole power half. This is the equation for junction width, okay? And this is an important equation. Now so far we have derived it. Now we'll consider cases where if the doping in P side is higher than doping in N side, then how will the junction profiles look? So we are going to concentrate on this particular graph and explain how it will be, okay? Let me take 3 cases. One, NA equals ND, and second case NA greater than ND, and third case NA less than ND. In these cases, okay, we'll see how the charge distribution inside the Pn junction will be. in the depletion region. We'll have a situation like this where Q and D equals Q and A. Okay, and the area under this positive charge curve and the area under this negative charge curve should be equal. So we'll have a case where Xn will be equal to Xp. So if we see W, which is equal to Xn plus Xp, in this case we'll have Xn equal to Xp. Okay. In the second case where Na is greater than Nd, we'll have a profile like this, charge distribution. The reason why we have more width in N side compared to P side is because if you look at a small width here, suppose say, let us take the same width into P side and N side. The number of charges that can be uncovered will be less in N type compared to P type. If you see same width here, the area under this and the area under this will not be equal. Okay, so for this amount of charge which is covered in P side, for that to be covered, you need to extend a longer length into the N type to cover that particular charge. So as a result, this, if the doping is higher in one side, the width in that side will be less compared to the other side where the doping is less, so the width will be higher. Okay, so we can say that if at one side doping is higher, that same side the width will be less, and the other side, if the doping is low, then the width will be higher. Okay, so in this case Xn will be greater than Xp. Okay, similarly if you look at the third case, okay, where Na is less than Nd. Okay, so Nd is higher and Na is lower. So if you look at this area and this area should be equal, and this is Q and D and this is Q and A. This is minus in all cases. Okay, so this Xp and this is Xn. So here Xp will be greater than Xn. So this is how it looks if it changes. Now take an extreme condition where suppose say Nd is very greater than Na. Okay, in that case the profile would look something like this. Okay, Nd is very greater, so Nd is very high, so the thickness will be like this. Okay, to equal this particular charge in P type. So if you see Xp with respect to Xn, W can be approximately written as Xp. In extreme doping cases where, I mean with respect to the other side where Nd is very greater than Na, the low doped side will be controlling the junction width. Okay, fine. So that's how it is. So if you have different doping profiles with respect to the other side, so you'll have different charge distribution things, and similarly you'll have the junction widths depending on which side is low doped. Okay, thanks for watching, and if you like the video please do subscribe, and thanks for watching again.